Couldn't keep the pose. Welcome to Circuits. We are going to be covering some very challenging topics today. Now, just as a recap, in our last lecture, we talked about some of the key features of RC circuits, LC, RL circuits, and the basic idea is that there is no instantaneous transition of power. We've only been dealing with circuits in steady state to date, and so really the idea is even if your voltage source is changing, your circuit is immediately adjusting to whatever the status is of that circuit, so that you end up with a circuit that's operating at steady state all the time. Okay. Now, just to give a recap, steady state is basically, it is stable long-term behavior. Okay. Now, when we talk about an RC circuit, we introduce a unique concept here. This is the idea of transients. Okay. Now, transients is something that it's unlike anything else that we've really faced. Again, we've only dealt with circuits in steady state. Transients means that the behavior of a circuit at any point in time is different from the steady state behavior or the long-term behavior. Okay, this is a time varying, meaning that it changes with time, response to changes in the system. Okay, now again, those changes in the system could be anything from flipping a switch. If you did have a time varying voltage source, it would create a transient response because the system is constantly trying to reach steady state, and as a result it is just introducing more and more transition periods between the state where it's currently at and the steady state where it's trying to get to. Okay? And this exists because it's a transition between I'll write that out as a transition between current and steady state solutions. Okay, so this is the idea of transients, is it isn't steady state. It is a time varying function that takes the solution from where it's at to where it wants to be. Okay, and that is transients. So we talked about that last time. This is kind of a really critical, important discussion because it's going to have mathematical implications here. Now, what we're going to do, and this is actually a lecture where I like writing this out over 2 entire boards. That's fun. I'll spare that for the RLC circuit, I suppose. What we're going to do, just a quick example where we study a voltage DC source that goes across a resistor and a capacitor. Okay, so here we have VS, R, and C. And the question is, and I guess what I'll have here is we will have at t equals 0, a flip is going to switch, and this is a charging circuit. Now, a charging circuit means we need some kind of initial condition. VC is equal to 0 at t equals 0. Okay, So this is called an initial condition because it identifies what is the behavior at the beginning. And as we've said, transients take it from what the initial condition is to what the final steady state behavior is. So really what we're studying is how are we going to be changing from this initial condition to the final steady state condition. Now, if you've read your book says that in DC steady state voltage systems, the capacitor behaves as if it is an open circuit. Okay? So, just looking at this, at steady state, we know that VC is going to be equal to VS. Because if there is an open circuit here, all of the voltage inside of that loop is going to just drop across VC. So we can say that already, just without even having to do any real calculations here. But what we're going to be talking about today is what does the transient solution look like? What does the shape of VC versus time look like? Okay, how does VC change from 0 to VS? 0 being the initial condition, VS being the steady state solution. Okay, now I did draw an exponential function last time. We're going to derive it this time because I feel like that's really important. This is differential equations, by the way. So if you have taken, or if you are currently in differential equations, or I guess Calc 2 is a class that has been merged with differential equations, advanced applications of mathematics here at Doane, you're going to have dealt with a little bit of this. And this is either going to be painful or it's going to be eye-opening. I usually hear that every year. Actually, I usually hear both from the same person, but it's whatever. All right, so here's what we know, okay? Now, the equations that we know are always true. All right, we have our component equation, we have our constitutive equations, which is basically the system equations, and then we have our component equations. All right, so here for our constitutive equations, we have KCL and KVL, and for our component equations, we just have the equations for those of 2. So we'll take KCL and KVL. I'm gonna go ahead and put this as node 1, 2, 3. So for KCL at 1, we know that IS is equal to IR. At 2, we know that IS is equal to IC. And then at 3, I should probably space these out a little bit, huh? IS is equal to IR. IR is equal to IC. IC is equal to IS. So those are our 3 KCL equations. They are constitutive equations because they have to do with the system. I'll move KVL over a little bit. And here we only have one loop. And because we only have one loop, so at L1, what we have is that VR plus VC is equal to VS. Okay, one loop. It's our KVL equation. So here again, if you look through the nodes, all of our currents are going to be equal in all of our components because of KCL. We have one coming in, one going out. One coming in, one coming out. Okay, and here we know that inside of one loop, all of our voltages have to sum to 0. So the voltage drop across the resistor plus the voltage drop across the capacitor has to be equal to this voltage source. Now, what I'm going to specify here very quickly is that these must be true at all times t. Okay? That means these cannot be violated. Just because we have a transient response does not mean that any of these equations are ever wrong. They're always true. At every time t, we can always go in and take measurements, check, and find that this is true. Okay? Whoa, I keep going out of focus here. These are always true. The transient response does not change. This is going to be true. Okay? Now, we also have a component equation that is also true for all times t. So here our component equation is the relationship between our current Yeah, current in the capacitor and the voltage in the capacitor. And then we have our relationship between our voltage in the resistor and the current in the resistor. Okay? Those are component equations because they're relationships between voltage and current. These are constitutive equations because they have to do with the entire circuit. All right? So now that we've identified these, and now that we know that they exist for all times t, what we're going to do is we're going to say, okay, we want to know how VC changes from 0 to Vs during the course of time. So we're going to solve for VC, all right? Now, what I typically like to do as a first step of solving this process is I like to go to an equation that has the source voltage in it. Here, this is Vs as a voltage source. Because Vs is a voltage source here, I want to keep this. I don't have Is. I don't know what Is is. Is is a calculated value that is derived from the behavior of the system by applying Vs to it. So we don't really know what Is is. We would have to do some calculations over the system, and this is going to change. That's a fun fact. Woo! I need to get a light on this. One sec. I think a light will help. This is usually where I initiate weird conversation. Yeah. I don't like blurry. I like living my life in the moment. Non-blurry. Alright, we'll see if that helps. As I'm blinded. Maybe it helps, maybe not, whatever. Okay, so all of these equations must be true. I'm going to identify an equation that has our source voltage in it. And ironically, this also has VC in it, which is nice. But I mostly care about this piece right here. Okay, so I'm going to grab an equation that has Vs in it. So here, Vs is equal to VR plus VC. Now I want to solve for VC. That's what I want. And because this is a system, everything is interrelated. We can actually solve for every component in terms of another component using the equations that I've already written up here, which is why I always start with the equations. Okay, so I'm going to have to figure out VR in terms of VC. Now, I go look for an equation that has VR in it. There's only one other one. It's this one right here. I'm just going to go ahead and Vs is equal to IR times R plus VC. Okay? Now, I don't know what IR is, so I'm going to go look for an equation with it. Well, we have the one that we just used, but if I plug that back in, I'll just end up going back up a step, so that doesn't help me. But I also have this one here, and I have this one, this one here. Okay? So I could either replace this with IS or with IC. Now again, I don't know what IS is, and I don't really want to bring in IS, so I'm going to replace it with IC. IC times R plus VC. Now I gotta look for an equation that has IC in it. Well, let's see, I could use this equation again. That would take me back up a step. I could use this equation, which would introduce IS into it. I don't want IS. Or I can use my component equation, which if I do that, Vs is equal to C dVC dt times R plus VC. Okay, now we've gotten somewhere. Now I have a function that only has a variable of VC on one side, and on the other side has a voltage source. That's what I want. This is a solvable problem, okay? And this right here is the, I don't remember the term for it, but this is the equation we're trying to solve, okay? It's a compound of all of the equations that we have, which, by the way, I gave you all of these equations day one in class. But it's a compound of all of these, and it takes, it's this. Now, how do we solve this? Well, how do you solve a system that has a variable plus its own derivative is equal to some voltage source? Well, we have to do some fun math here, okay? So, I'm going to introduce a couple of concepts. Number one, is this fun idea of what's called a I have a very specific term I like to use for this. Of course, I'm going to draw a blank right in the middle of class. You guys are going to watch me think. Thinking. Yeah. I know exactly what I want to say, but I don't know what the second word is. So here, it's got to have the same exact time variation, okay? All equations, it turns out, have to have the same time functions, okay, on both sides. Okay, so here if I do x equals 5, what I'm implying here is that 5 is a constant, which also means that x itself is a constant. So if I were to write out x of t is equal to 0t plus 5, which is the constant, right? It does not change as a function of time. In fact, we can continue to write out x of t. X of t is 0 times cosine of omega t plus 0 times sine of omega t plus 0t squared plus 0t cubed plus 0t to the fourth. We still have all of these 0 components because the only one that matters to us is this constant, 5. So that by nature, it has the same time function on both sides of the equation, okay? And all of these other components are forced to be 0 because on this side of the equation, it's 5 as a constant plus 0 times cosine omega t plus 0 times sine omega t plus 0 times t squared, 0 times t cubed, 0 times 1 over t. And we have a whole bunch of zeros on both sides of the equation that quite frankly we don't even write out. Okay, so that's just a very simple example. To take that in other terms, if we have x plus y is equal to 5 cosine omega t, where omega is a constant, what we have here is we have one of two conditions that can be true. Number one, both x and y are functions of cosine. Okay, that can be true. We actually can come up with a system where, okay, if x is 2 cosine omega t and y is 3 cosine omega t, that sums to 5 cosine omega t. That's condition 1. Okay, but condition 2 is x plus y sum to create a cosine function. Okay. Now, this becomes a lot more difficult because what two functions sum to equal a cosine function? Well, we can't have, if we're plotting in our function values versus time, our cosine function is going to look something like this, okay? So this is our cosine function. I'm going to switch colors. I'm going to look at possible functions that otherwise could be done with this. We could have a t equation where it's a linear relationship with time. This is unfortunately not going to work because this is increasing with time, and this one oscillates around 0. So any function t squared, t cubed, t to the fourth, t to the fifth, this won't work because you can't really sum and create a cosine function from something that increases exponentially the larger it goes with a larger value of t. I mean, we still end up with a value of 0 here, periodically. So how do we sum so that some function plus another function is equal to cosine? Well, there are some trigonometric functions that do sum to cosine. Well, we're actually going to talk about those in this class. But in reality, what you end up with is you're only stuck with a sine and a cosine. Only sine and only cosine sum to only sine and cosine. That's all we have. Okay, so we know that x and y either both have to be cosine or have to be some function of sine and cosine. That's the only thing that can be. Because our time functions have to be equal on both sides of the equation. We cannot have a t without having a t over here. We cannot have a linear relationship with time without having a linear relationship with time over here. It can't happen. It's impossible. You can't sum sine and cosine functions, two of them, and get a linearly increasing function. And you could actually have an infinite sum of sine and cosine functions that equals a linear function. That's a different story. It's a Fourier transform. It's kind of an interesting concept there. But you cannot have t squared represented by sine of x plus cosine of x. You just can't. So these two principles have to stay true. X and y either have to be functions of cosine, or x and y have to sum to create a cosine function. Okay, now there is a third condition that is possible. And the third one is either, well, and this is kind of a piece of two, I should say. X and y are 0. Okay, which is also a possibility. Or the flip end of it, x plus y is equal to 0, which can't be true here because it has to be equal to 5 cosine omega t, but that is a condition of the second one, that is that they could add to 0. All right, so how do we take this and make something useful out of it? Well, as I said, all equations have to have equal time functions on both sides of the equation. All right, now what we're going to go ahead and say is we're going to split this out. There's an easy solution to this. If VC is equal to 5 and VC is a constant, dVC dt is equal to 0 and Vs is a constant. Okay, that's an easy solution. If Vs is equal to constant, then Vc is equal to constant, which means dVc dt is equal to 0. Okay, which is finding a way to turn this piece into 0 so that one function that has the same time function as the other side of the equation plus 0 that works. Okay, we talked about that already. There's an infinite number of zeros in every equation. Okay, so this is one solution. This also happens to be the steady state solution. We know that Vc is equal to 0 at t equals 0, which means at t equals 0, this has to be 0. Which means at t equals 0, we have to have a derivative that is non-zero. And that's for some values of t. Okay, now this poses a problem, because if dVc dt is not equal to 0, that means Vc cannot be a constant, and it also means that Vc cannot be equal to 0. Okay, so this poses a huge problem, because now if I'm going to sum this value plus this value is equal to Vs, I now have to get the sum of those two variables to equal a constant. And we only have those three conditions, well, the two conditions that I wrote up here. Either they both have to be functions of that same time function, which meaning this one has to be a constant and this one has to be a constant, which is impossible because this is a derivative of that. And if this is a constant, this is 0. We can't do that. So our first condition can't be met. Our second condition has to be true, and that is these two must sum to create this. And that's what we're going to be going with, okay? We're going to have a component from this that is a constant, but we're also going to have a component of this that is not a constant. And both this plus this are going to sum to 0. Okay? So then the question becomes, what function plus its derivative have the same time function? Same time derivative function. What function has the same time function as its derivative? Okay. Well, the derivative of t, if we just have ct, the derivative of that is just c. That doesn't have the same time function. If we have c over t, the derivative of that is negative c over t squared. Well, that's not the same. We have log c, and the derivative of that, well, that becomes really gross, like 1 over c. Okay, so unfortunately we're running into some problems here. There is exactly one function that we know of whose derivative has the same time function, and that is e to the t. So if I have e to the constant times t, and here this will be c2, this will be c1, the derivative of that is c1, c2, e to c2, t. Okay, they have the same time function. If c1 and c2 are both 1, it becomes e to the t. The derivative of that is e to the t. Now this is something that can actually help us out greatly. When we're going to solve this problem, we're going to split this problem into two pieces. One of which is the steady state solution, okay? Which ends up being, we're going to force VC to have a component to it that has the exact same time function as VS. The second piece to that is we're going to have a transient piece. Okay? And that transient piece is this plus this plus its own derivative has to be equal to 0. Okay? So let me clean up my board a little bit. I'm going to leave this up here. I'm going to write this equation because this is really the only equation we need at this point. I'm going to go ahead and erase all of this. I feel like in this class you just spend most of your time looking at my butt. Although, if I think about it in a very weird way, you spend most of your time looking at my butt anyways. Let's be honest here. It's gross. Doesn't help that I love whiteboards. So we have CR, dVC, dt. Now here I just moved the R to the front side of the equation just to combine terms that are being multiplied plus VC. Okay, so this is the equation that we're trying to solve. Okay, that's this equation. And we have two pieces to what we know our solution is going to be. Okay, so we know that our solution is going to be a transient portion and a steady states portion. If I write it wrong, I could write potion. There we go. Steady state potion. Be in steady state. Okay, so here, what's critical about this piece is that the transient portion of this solution has to sum to 0 with its derivative. Okay, it has to satisfy that equation. The steady state portion of this one has to have the same time function as and here we're going to call this the forcing function. Forcing function! If you do your reading assignment, you will have read the word forcing function. It's very much applicable to this. So here, forcing function. So here, transient portion of our solution is going to sum to 0 with its derivative, which will ultimately wipe out our time varying need here. On the flip end of this, we have a steady state portion, which will remain here. Okay, and both of those are needed. Nice. Okay. So I'm going to go ahead and name these. All right. This transient portion, what I'm just going to call this is called the homogeneous solution. Okay. And what a homogeneous solution is okay, so if we force the forcing function to be 0, how would this system respond to suddenly being forced to 0? Okay, now there's a fun little bit of math we have to do with this, but that's basically what the homogeneous solution is what is the transient piece? How does it change? We can ignore Vs, because Vs ultimately really only comes into the steady state portion, and then we only focus on how does it change from one system to another. Here, we know it has to increase 5 volts. So what we're going to do is, for this homogeneous solution, we're just going to assume, or if Vs is equal to a constant 5 volts, we're going to assume that it has to jump up a value of Vs volts to 0. Okay? And it makes our math a little bit nicer when we assume it that way, but that's basically what the homogeneous solution is. We're going to ignore what Vs is. We know that this is going to increase a total of Vs volts, and because of that, how does this system have Vc increased by Vs volts? How does that happen? Okay, now if in our initial condition Vc was not equal to 0, you'll notice that our homogeneous solution would be maybe jumping up 3 volts. You know, if Vs minus Vc is only equal to 2 volts, if there's a small charge on the capacitor prior to plugging it into the system, this is going to change a little bit as we go plug this in. So really all this is how much does that Vc have to change? And that doesn't depend on Vs at all. It really doesn't. Okay, and over here, this is going to be called the particular solution. And in our particular solution, this is, what is the steady state behavior of the system? Okay, so we already actually know the answer to this. we plugged it in right here. We just, without having done any math, we know the steady state solution is going to be, the particular solution is going to be Vs. Yeah, that's fun. We already know half of this equation. But it's solving for the homogeneous solution that gets a little bit crazy. Now I've set up this problem. What I'm going to do is I'm going to go ahead and pause this video so that you can go back and watch this one. I'm going to solve this equation in this system in the next video.